Hello, AP Chem. Welcome to your gases station investigation that I am doing online through Edpuzzle. So here we go. Miss Brown here, and we are going to learn about all the things that we need to factor in when we are thinking about gases in chemical terms, right? So we've already seen that some reactions produce gases, so it might be important if we want to know how much of a gas we're going to make, or if we're going to be making gas and putting it in a container, will it make that container explode, right? That's when chemistry is exciting. So what we'll be doing is going through a series of small activities that show a relationship. So your goal today is to see what I am manipulating, what variable I'm manipulating about the gas, what then responds, and then what the relationship is. So is that a direct relationship? Is that an inverse relationship? And then what we'll be able to do is all of these variables that affect gases, we'll be able to combine into one awesome, easy to use equation that you're going to use hopefully for the rest of your life. So, let's dive in. You might want something to just take notes on as you follow along. There will be questions as we go in the video. Here we go. Here we have a balloon. I have put some gas into it, okay? And so we are going to look at some relationships for this balloon. So here's it to begin with. Initially, this is how much gas is in it. And so what I'm going to do is I'm going to add some more. Okay, I added more gas. That's my manipulated variable. What variable responded about the gas? Okay, so think less about the balloon, think about what's going on inside. So I just blew up a balloon, right? And we're thinking about what is proportional to each other there. So what we found out was that I was increasing the number of moles, right? And then we were looking at what changed in the balloon. So the temperature didn't really change. The pressure, the external pressure on the balloon didn't change. And what we learned in class yesterday is that when you have a flexible container, the flexible container compacts and expands to meet the external pressure of what's going on outside. That's what external pressure means, right? So if it's small, it has the same pressure as on the outside, even if it's big. And then at a certain point, to match the external pressure, maybe the balloon would have to get too big and it would pop. But anyway, pressure is being held constant, temperature is being held constant. So what we're looking at is how the number of moles, which we're using the letter N to signify, right? How that affects the volume of our flexible container, right? So we're looking at N and V. So what we've kind of done so far, I think when we've talked about proportionalities in class, if we said, okay, as N increases, V increases. So if you put more stuff into a flexible container, its volume will increase. That just kind of makes sense, right? If you hold everything else constant. We actually have another way, more mathematical way to write this. So let's say we don't actually know what the slope of this linear relationship is, right? Like if N goes up, does volume go up by 0.2? Does it go up by 30? We don't know that, right? And those are different units, moles and volume, which is usually in liters. We don't know that. So when you don't know that information, instead of using an equal sign, we're able to use something called a proportionality symbol. So there's my N. A proportionality symbol looks kind of like a lowercase Greek alpha. Oh, this is not good. It's okay. It's all right. And then we just say N is proportional to V. Pretty nice. Okay. But let's take this just one step further. Let's say we do want to use an equal sign. Well, we know that there is, if we're saying these are linear relationships, these are directly proportional, that if we multiply V by some number, it will get us the correct units of N. So how we would write this is that N is equal to, let's use K. K is a good letter to indicate a constant, okay? K multiplied by V. So it's still true in our mathematical equation here. If V goes up, N will go up just by this proportionality constant, K, which we don't need to figure out right now. Okay. So here we have our same happy birthday balloon. Looks a little sad because I didn't quite blow it up that much. We're going to try a couple things here. So to start, I'm gonna put this balloon in a hot water bath. So let's just look at it. Let's make sure we're all checked in. Okay. Let's put this in the hot water bath and see what happens. How hot is my hot water? It's pretty hot. It's pretty warm. It was boiling just a little while ago. Are we seeing anything change? I guess I should hold it in there. Seems to me that the balloon is getting bigger in the hot water. Okay. So let's just think about, what am I manipulating about this gas? And then what is responding to that change? Okay, that seems pretty good. Let's put it in the cold water bath. See what happens. Definitely smaller, right? Okay, so think about it. What did we manipulate? What responded? And then what's the relationship? Is it direct? Now we're going to mathematically represent what happened to the balloon when we put it in cold water versus warm water, right? So in the balloon, what are we holding constant? Well, we're holding the number of moles constant, right? And the pressure is constant on the inside and the outside, right? So what we're changing is temperature, and we're going to change the volume, right? So what was the one we were controlling? Well, we were controlling the temperature, okay? So temperature. So what happened to, if we increase the temperature, we went from the cold water, we actually went from hot water to cold water. So let's say that we decreased the temperature. What happened to the volume of that balloon? Well, we saw that it got smaller. So as temperature decreases, volume decreases. Is it true that if temperature increases, volume increases? Heck yeah, it is. Okay, so we have a handy little proportionality symbol that we can use to write this. So T is proportional. Whew! Oh, that was bad. Oh well. T is proportional to V. Okay, so as T increases, V increases, and vice versa. Okay, so now here's what we're going to do is let's use our proportionality constant. So now we're going to say T and use an equal sign. Why couldn't I use an equal sign up here? Because temperature and volume cannot be equal. They are not the same units. It makes zero sense. There is some number by which we multiply V to get the correct temperature, right? And we don't need to figure it out because we know algebra. So we're just going to say, hey, there's a constant. We can imagine that it is a number. Cool. So T equals kV. And K would change. Like if we're doing volume in milliliters versus volume in liters, it would change. Yeah? All right. All right, here's a new one we're going to try. I have these marshmallows that have been in this room for a long time. They're a little stiff, but that's okay. We are going to make a nice little marshmallow friend with a nice little smiley face. What's that? That's pretty cute, right? Okay, name them something. It's a good marshmallow name. Martha the marshmallow. Okay, so marshmallows going in this syringe. Okay, so I am going to try and cover this. So let's think about when I depress the plunger, what variable am I manipulating here? All right, okay. Let's see, I think, there we go. That's what I need to do. Okay, so I've got this covered here on the end. And when I open up the plunger, what's happening to that marshmallow versus when I let it go and open, let it go and open, right? Okay, so think about what I'm doing. I'm changing the volume, right? And what is responding? And our poor little marshmallow friend is a little bit beat up, but what are you gonna do? Martha the marshmallow was stuck in a syringe, right? So what are we changing here and what's responding and what were we holding constant? Okay, so I put my finger over the end of the syringe, right? So as I was depressing the syringe and expanding it, we were trying to hold the number of moles constant, right? We were keeping the same amount of gas in there. I also didn't affect the temperature, right? I didn't put it in the hot or cold water bath. So we're looking at volume and pressure, right? So when I was changing the syringe, I was changing the volume, right? So I was manipulating the volume. And as the volume decreased, when I depressed the plunger on the syringe, what happened to the pressure on the marshmallow? Well, the marshmallow saw the pressure increase, right? Our poor little marshmallow got pretty smushed up by all that pressure, okay? So here we have an inversely proportional setup, right? So if I decrease the volume, the pressure will go up. If I increase the volume, the pressure will go down. So here's what we're going to do, how we're going to write that. We're going to say V, and we still use the proportionality symbol, but then it's 1 over P. Pretty handy, right? Okay, so that's showing that those are inversely proportional. Could we have written it P is proportional to 1 over V for sure? Now what we can do is we can put in our K, which we should be getting pretty good at. And instead of saying K times 1 over P, I'm just going to write K over P. This is the same math. Okay. Same numerically. Cool. So pretty nice. Another thing we could do too is if we want to if we don't want to have a denominator, right? Sometimes we I don't know. I don't like it when I'm writing equations. Let's keep it as straightforward as possible. V times P equals K. And something I really want to point out in this unit to get you good at thinking about equations in your future. When you have two things multiplied on the same side of an equation, that means that they are inversely proportional, right? So if we hold everything constant on the other side of this equation, if V goes up, P has to go down to keep everything constant. Okay, I hope that helps. We're going to do one more. I just brought this one out of the cold water, and you try and create a seal with the water and the dime. You only have so much time to make this work. So let's just see here. Okay, so I got my water and my dime. I'm gonna try and heat this up just with my hands and not move the, okay, good, the dime's right there. So let's see if anything happens. To try my hands. Oh, it did burp a little bit. You just saw it. Okay, it's still on there. Let's try putting it in the hot water bath and see, because the seal is still there. Okay, so I'm gonna try not to move it because I don't want to mess up that seal. Okay, so let's just see if I can be really careful here. Get this down in there and see. There we go. Did you hear it? Just burped. There we go. Oh, the dime just moved. Okay. So think about what I manipulated and what responded. How did that dime get pushed up? Our final one. So this is our dime on the inflexible container, that round flask that we had, right? So we manipulated the temperature and we increased the temperature. It was in the cold water bath, and then I put it out, tried to heat it with my hands, wasn't quite enough, and then we put it in the hot water bath. So we increased the temperature. What happened inside of the container? Well, the volume didn't change. The number of moles didn't change inside the container. What we did was we changed the pressure. And how did we see that? Well, the pressure got so great that it was able to push a whole dime up just by changing the temperature, which is pretty cool, I think. Okay. Expansion and compression of gases, how engines and refrigerators, all sorts of cool stuff work. So temperature goes up, pressure goes up, which makes sense. You think about this, it's like when they say don't throw an aerosol container into the fire, it will explode, you will get shrapnel in your face, that's terrible. When you increase the temperature, it increases the pressure. This is probably one that is most intuitive for people to understand. Remember, pressure, we're thinking about all the particles in a gas hitting the insides of a container and pushing on it, and it matters And we're thinking about the area too. They have so much area to hit. So if you're in a really big container and you only have a few particles, your pressure isn't going to be that high. Okay, sorry, I'm going on a tangent. So let's use our proportionality symbol just because we all love it so much. I know you're just going to love me for teaching you that. Okay, temperature is proportional to pressure. But now we can say, hey, temperature is equal to K times P. Again, pressure and temperature, you can't convert them into each other. We need some sort of number to associate those two. And if you were a scientist like 500 years ago, all you had to do was figure out what K was and you could have something named after you. Not anymore, unfortunately. Let's just review these together. So we had a couple of stuff. We said initially, we were just looking at balloons. We said that as moles went up, we said the volume went up. Okay. Can we think about pressure too? Let's say we increased moles in an inflexible container. What do you think would happen? Is number of moles going to be proportional to pressure or inversely proportional to pressure? Well, I would say directly proportional, right? You put more stuff in, you're going to have more pressure. Okay, so we have a couple of relationships there. Then we looked at the balloon and ice, right? So we said that as the temperature went up in the balloon, the volume went up. So temperature is proportional to volume. Okay, and we have our syringe. We said as we change the volume, this one was our weird one, right? K over P. So those were inversely proportional. Then we have our last one here. T is equal to K over P. I'm going to teach you, before we move on to the big point of this whole lab, I'm going to teach you one quick little thing that will help you immensely on the AP exam. They don't require you to know it because you can use a much longer equation, the one we're about to use, but I'm going to teach you a little bit of a shortcut. And let me get my pen going. Let's change the color. Let's do blue. Sounds good, right? So here's something that we figured out, right? So if we said P and multiplied by V equals K. Do you remember doing that? I hope you do. Okay, here's what's really interesting. Say you have something, some sort of system, some sort of gas that you just collected from a chemical reaction, and it has some sort of initial conditions, P1 and V1, right? And then you have some final conditions, P2, V2, all right? And those are equal to the same constant, right? It's a constant, so it should be the same in every situation. So doesn't that then mean that P1, V1 is equal to P2 multiplied by V2? I would say yes. Now, this only works when everything else is held constant. So if you're trying to use this in a problem, say I said, okay, you have a balloon. It has an initial pressure of this, an initial volume of that. Its new pressure is this. What's the new volume? Easy calculation, right? Just quick little algebra 1 move right there. You just have to make sure that everything else, the temperature is being held constant and the number of moles is being held constant, right? This is pretty handy. We can do this with a lot of things. So we can do this with volume and temperature. So remember, volume was equal to K times T, or T is equal to K times V. Either way, any way we want to do this. So that means that volume over temperature is equal to K, which then is equal to V2 over T2. So same thing. If pressure is being held constant, if number of moles is being held constant, if you have 3 of these numbers, you can get the other one. Okay, and our last relationship that is nice to know is very similar. Pressure over temperature. That T got a little away from me there. Sorry about that. Is equal to K. P1 over T1 is going to equal P2 over T2. Again, as long as volume and number of moles is being held constant, this stays true. We can actually put this all together, and this is one thing that you are going to want to have in your brain that is not on your green sheet for AP Chem. We can put all this together in something called the combined gas law, okay? So I'm going to put it together here under this line. So here's what we see. Look at these relationships. P1 times V1 equals P2 times V2. And then P and V have the same relationship to T. All right. So what we can do is we can combine these. And this is called our combined gas law. I'm teaching you this because it can save you time on the AP Chem exam if you don't need to use what we're about to learn called the ideal gas law, which can have you calculating more. So if you have an initial and final situation and we're holding number of moles constant, boom, you got this. And what's nice is you don't need to memorize all of these little pieces, which all have names. We've got Charles' law and Boyle's law, and we don't need to memorize all of these, right? Because if you know this relationship, they're all embedded here. Okay. And what's cool is, let's say the volume is staying constant for something. Well, if you just ignore these parts because they're staying constant, well, then you have this nice P1, T1 relationship. It's all there. Okay. So that's a little trick for you. Let's do one combined gas law problem just to see how this is going. So here's what we've got. They're telling us that we have a volume, a 113 liter sample of helium. Don't really care if it's helium, at 27 degrees C is cooled at constant pressure to negative 78 degrees C. Calculate the new volume. So this is, we're going to use we have an initial and a final, right? So we need to be using our combined gas law. Forgot what it was called. Super sorry. So here's what that is. It's P1 V1 over T1 is equal to P2 V2 over T2. All right. So we are holding pressure constant, so we do not care. So our relationship is V1 over T1 equals V2 over T2. So let's just write that out. We're going to start with a 113 liter sample, and then we need to put T1 down here. Now we have some issues though, because it's hard to do these proportionalities when you go negative. That is why we always have to use Kelvin. So to convert these into Kelvin, we're just going to add 273.15. So 27 plus 273.15 is going to be 300.15 K. All right, and then that's going to be equal to V2. We don't know what that is, but that's over negative 78. So if we take 273.15 plus negative 78, okay, we're going to get 195.15. Cool. All right. So let's just solve. So 113 divided by 300.15. Okay. And then we're going to multiply that by 195.15. And I got that our V2 is going to be equal to 73.4697. Let's think about sig figs here. We have 2 in this 27 degrees, so that's all we can do. So it's going to be 73 hard stop liters. Let's just double check. Does that make sense? We reduced the temperature and the volume decreased. Yes, we saw that in the lab. Makes sense to me. Here we are. We're at the point of the whole lab. We are going to create something incredibly useful. Are you ready? So what we've done is we've looked at all the individual relationships. We've looked at an equation that we can use for initial versus final in terms of some of these gas relationships. And now we are going to put together the big final equation that really helps us. Okay. So what we had last time, where we left off with, let's do green. Green sounds kind of nice right now. What we left off last time with was we had this relationship. We kind of put this together. We said P times V over T. Well, that is going to equal some constant K. And what's cool, K is weird. What's cool is when P has a constant and V has a constant to get between these, and we also have T, when you combine constants, there's still just a constant. The number just changes, right? If you're multiplying multiple constants, it can just become one new constant. Okay. What we need to do is we need to put the other thing we care about in terms of gases. We need to put number of moles in here. Okay. So let's just think about where number of moles might go in terms of its relationship to these things. So what did we figure out? If we put in moles, what happens to volume? Let's just think about that relationship. So if you have a flexible container, you hold temperature constant, you hold pressure constant, you put more moles in, Well, the volume's going to increase, right? If we're in a flexible container, which is where the volume is allowed to change. How about number of moles and pressure? If we're holding temperature and volume constant, rigid container, what's going to happen to the pressure? Well, it's going to increase, right? So what's that relationship? If P goes up and N goes up, and we're going to be having a constant, well, N's going to need to be in the denominator, right? So what we should see here is if P goes up, V would go down, yeah? So then we have K, right? Inverse relationship right there. And then here's our direct relationship, T multiplied by N. Is that okay? I don't use multiplication symbols anymore. In science, we don't really write them in, just trying to make it clear. So P multiplied by V over T multiplied by N. Let's check that NT relationship. So let's assume pressure and volume are being held constant. Are temperature and number of moles proportional? Let's do a thought experiment. So you have a rigid container and you are holding the pressure constant in it. We don't even need to talk about how you would do that. We're going to hold both of those constant. If you pack more moles in and the pressure doesn't go up, the temperature is going to need to go down. Otherwise, the pressure would go up. There's no other way to hold the pressure the same. So if you increase the number of moles, the temperature goes down. Whoa. So those are inversely proportional. So we have a good statement here. And what we've done is this is final. This is it. These are the 4 variables we're thinking about for gases. What we've done is we combine all of those K's together into something called R. It's the ideal gas constant. I want you to find it on your green sheet right now. I'm going to find it on mine. So I have my green sheet right here. It's over here, gas, liquids, and solutions, right over here. And this is what you're given on the AP exam. Gas constant. Oh my gosh, they gave us 3. So there's one, the 8.314 joules per mole Kelvin. We're not going to use that yet. We will soon. There's this other one that's pretty straightforward. The second one down. It is I put myself into eraser mode. It's pen mode. So R is equal to, and they called it R is equal to 0.8206. I actually do not care what the number is. Here's what we care about. We care about these units. These units are amazing. So let's check them out. They're saying liters multiplied by atmospheres. And then inverse moles, so per mole. Ow, that is an alien M. Oh well, per mole Kelvin. So let's see how this works here. We decided to make KR, and let's see, do these units match our variables over here? Pressure is in atmospheres, volume is in liters, N is moles, temperature is in K. And remember, all of our gas stuff, we are doing temperature in K. We do not need those negative signs messing up our math here. Okay, so this is our equation. This is called the ideal gas law. Here's how it's typically written out. PV equals nRT. Different than our combined gas law, we could use this to do some final and initial stuff, but what we're going to be able to do is if you know 3 of these, you know the other one. So if I say, hey, here's a gas, here's its pressure, here's its volume, here's the number of moles, tell me the temperature. All you have to do is make sure that your units are correct and you are good to go. So let's practice a couple problems. All right, here's our problem. Sorry, my camera's covering it up just a little bit, but here's classic PV equals nRT problem. And they don't tell you immediately that what you need to use, right? So when you're looking at a problem like this, on the AP Chem exam, here's what I would do. Okay, we're trying to solve for temperature. So I'm just going to put a big old T there. They're telling us N, okay? They're giving us pressure, and here's our volume. Looks like I have 3 of the 4 things, and so I can easily solve for pressure using the equation PV, maybe. There we go, pen mode, equals nRT. So a couple things we're going to want to do. Check what units all of these are in to make sure that you are getting the correct units out and everything works with R, because R must match, right? Because otherwise you wouldn't be converting into the right thing. So our pressure is 1.25 And what I want you to do right now is I want you to write out your units. That's just the rule, okay? So 1.25 atmospheres times 25.0 liters equal to N, 2.10 moles. And then we have our 0.08206. And let's look at the units for that. So the units are liters, atmospheres, mole per mole K. And then we are solving for T. Big old question mark there. Let's cancel out our units before we do anything else just to make sure we're good. So liters on this side, liters on that side, we're good. Atmospheres here, atmospheres there, moles here, moles here. We're solving for Kelvin, and that makes sense because there's our question mark T. Okay? So all we need to do is punch this into our calculator. So here we go. Get an answer. 1.25 times 25. All right, and then we're going to divide by 2.10, divide by 0.0826, and I got that the temperature is going to be 180.1568 units of Kelvin. We're just going to be used to that. Now, sig figs, what do we've got? 3, 3, 3. Our gas constant has 4, so I'm going to need to cut this off at 3. So I would write 180 decimal K, or 1.80 times 10 to the second K. Cool. Let's try one more. All right. I'm ready to go back to blue. How about you? So here we go. We have a question. We're solving for volume in this situation. They're giving us grams, which we know we can convert that to moles. That's fine. We'll call it N, but we got to remember we have to convert to moles. We're talking about O2 in this situation, and we've got 28 degrees C. So many conversions. Oh, well, luckily a Celsius to Kelvin conversion is pretty easy, and we're at 0.998 atmospheres. So let's just set this up, and then we can work on our conversions. So pressure is 0.998 atmospheres, and then we are solving for volume. We do not know what that volume is going to be. Let's work on this 5.03 grams. We need to get that into moles. So 5.03 grams, and I'm glad we're doing oxygen. I'm going to ask you a question in the ed puzzle right here. We're talking about oxygen. How many grams are in 1 mole of O2? Okay, I hope you said about 31.998. I've been seeing this a lot creeping back in. If it's O2, you got to double that molar mass, right? So let's figure out how many moles that is. So 5.03 divided by that 31.998. I'm getting that we have 0.157 moles of our O2. Okay. Ideal gas constant, 0.08206. That's liters, atmospheres. Yeah, I'm going to keep writing those units, team. You should too. Moles, Kelvin. Okay. And do we know the temperature? We do know the temperature. It's 28 degrees C. I need that in Kelvin. We do know that 0 degrees C is, that should be, let's just do a little undo there. 273.15 K is equal to 0 degrees Celsius, and they use the same gradations, right? So all we have to do is add 28 to this. Okay, so 273.15 plus 28 is 301. You're like, Ms. Brown, you're doing that on your calculator? Yeah, on the exam, I would do everything on my calculator. Unless you're really always confident and don't get in any test brain. I think just when you have your calculator during the FRQ, do it. 301.15 K. Right? We don't really know that, but that's okay. 301.15 K is what we're working with. So let's put this all together. What do we need to do? Personally, what I would do is if I have all the numbers on one side, I would just get that and then divide by the 0.998. So let's do it. 0.157 multiplied by 0.08206 multiplied by 301.15. And then we're going to divide by 0.998 atmospheres. We're going to get, I got an answer of 3.8876, and that's liters. And if we look at sig figs, looks like we have a controlling number of 3, so 3.89 liters. Okay. Did our units work out? Let's just double check this. Let's use the gold. Okay, atmospheres, numerator. Liters is what we're solving for. Moles and inverse moles, and then Kelvin, inverse Kelvin and Kelvin. Okay. Looks good to me. Not that smile. It's kind of cute. I got some wonky eyes.